Hello, 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 everybody, and welcome back. We're still looking at the 2009 Galois paper, but we're actually going to finish it up in this video because we've made it to question number 4. Okay. So question number 4. Looks like we have quite a bit of reading ahead of us, so they're going to try and explain a concept. And this actually usually bodes well. First of all, this tends to be a nice form for questions 4 on the Galois and the Hypatia, which is the grade 11 version of the paper. Usually, and it also happens a lot usually on Euclid 10. What happens is they'll introduce a brand new concept and see how quickly people can cope with it, how quickly people can deduce things about it and reason things about it. And usually, even if you're not strong and you're not someone who can get questions 4 or question 10 on the Euclid, when they present a question like this, you can usually score a couple extra marks just by looking at A and sometimes B if it's a 4-parter. The last B3s on the Canadian Intermediate and Canadian Senior also do this. But you can usually they'll present a brand new concept, and usually A part is 1 or 2 marks, just a very quick. Okay, here's the concept. Did you understand it enough to perform this very basic calculation, a very basic decomposition, or very basic construction or something like that? It's usually worth a look. Even if you're someone who says, no, there's no way I'm going to get question 4 on the Galois paper, you still might get 4A. Okay? So, it's a trend that I've noticed in recent years. And it's good for a mark or 2, usually. Okay? Even if you don't understand it well enough to do the D part down here. Okay. If m is a positive integer, the symbol m factorial, if you're not familiar with m factorial, this is what it's called, m factorial, is used to represent the product of integers from 1 to m. So it's m times m minus 1 times m minus 2 times m minus 3 all the way down to times 4 times 3 times 2 times 1. For example, 5 factorial is 5 times 4 times 3 times 2 times 1, which can be calculated as 120. 4 factorial is 24. 6 factorial is 720. These are numbers that I am familiar with. So they tend to pop up a lot, so hopefully this isn't your first time seeing factorials. I'm just taking a look at my calculator that I have on hand. I don't see a factorial button, but I know some calculators do have factorial buttons, which can be quite nice and helpful. Not necessarily for this question, but in general. Okay, so factorials, there you go if you haven't seen them before. Some positive integers n can be written in the form n is a times 1 factorial plus b times 2 factorial plus c times 3 factorial plus d times 4 factorial plus e times 5 factorial. And so if you're not familiar with this, and I'll be honest, when I wrote these contests, I was not familiar with this. I was familiar with factorial. I think you should be if you're going to be writing even the Fryer paper. But this is actually, I believe, called the factoratic numbering system or base system or something like that. Okay, so if you're interested in learning more about this, here's what it is, and you can go find another resource about it. I'll finish reading up the question. I'll talk a little bit about more of the factoratic number system. However, I will not do the question with any of the knowledge that I have. So some numbers can be written in this form, apparently. In addition, each of the following conditions is satisfied. A, B, C, D, and E are all integers. A is between 0 and 1, B is between 0 and 2, C is between 0 and 3, D is between 0 and 4, and E is between 0 and 5, and notice that E is next to the 5 factorial. Okay. This is the factoratic number system. It's, as I say, it wasn't something I knew about in high school, but I have since learned about it. It doesn't have the most uses. It's sort of like base 10, or you might be more familiar with, like, base 16 or base 8 or binary, which is base 2. They're just different ways of expressing numbers. Okay? And, some have some advantages. For example, computers use binary, just ones and zeros, on and off. Very easy to program that with, electrical currents and flipping little switches and things like that. But other things like base 16, that's how we represent colors in hexadecimal, so that's hex codes if you've ever done anything with websites. And so different number systems have their charm. We use base 10. You know, you go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but there isn't a unique symbol for 10. It's 1 and then a 0, 1, 10, and 0 units. And then you get 1 10 squared, 0 tens, and 0 units for 100, and so on. But the factoratic number system is a little peculiar in which, because there isn't sort of a fixed base, it changes. You know, you get the units digits are the 1 factorials, then where you would imagine the tens digits represent how many 2 factorials, then how many 3 factorials. It can be useful when you are writing things out, when you are sort of programming and enumerating permutations and I believe even combinations, which it comes up every once in a while when you do computer programming. And I do think, if you haven't already, assuming you're actually in grade 10, if you haven't looked at computer programming before, I do recommend you try it. First of all, it's a useful skill to have, period. It makes a great minor or even major in university. But as mathematicians, we're actually really good at it because we think very logically, and that's all computer programming is thinking logically and trying to set up, okay, I want this end goal, how should I get it? And you sort of make the little roadmap and go from this. It hones your algorithmic skills, you're thinking through processes, which can actually be very helpful in math as well. So there's my pitch for computer science, and that's where factoratics actually have come up for me. I did some combinatorics programming in part of my thesis. And nothing really interesting, but factoratic number system, I recognize it, and if you've seen it before, you'll recognize it here too. I don't know how much it's going to help, and I'm going to proceed through the question as though I didn't know anything about the factoratic number system. So let's just go through it. We got 4 questions here, A, B, C, D. A, determine the largest positive integer n that can be written in this form. Again, this, A part should be fairly simple and basic, and it is. They tell us our upper bounds for A, B, C, D, and E. Those are the only things that can vary with our numbers, so the biggest n will just be the one that has the biggest A's, B's, C's, because they're all positive integers. And we just write that down. So A, B, C, D, E are, well, they're not positive, but they're not negative. As are 1 factorial through 5 factorial. And this is all I would write. So the biggest n is found by taking the biggest A, B, C, D, and E values. So n would be 1 times 1 factorial, 2 times 2 factorial. I believe, if I remember correctly, this is going to be the next factorial, so 6 factorial minus 1. There's my knowledge of the factoratics, but that doesn't actually help me because I need to write this up and I need to actually do this calculation. 1 factorial is 1, so 1 times 1 is 1. 2 factorial is 2, so this will be 2 times 2 is 4. 3 factorial is 6, so this is 18. 4 factorial, I've mentioned, is 24, so 4 times 24 is 96. They give us 5 factorial in the question, so that'll be 5 times 120 is 600. And now we add this up. The 4 and the 96 is 100, so that's 100 plus 600 is 700. 1 and 18 is 19, so this is 719. And 6 factorial is 720, so looks like I was right. Okay. But that's sort of where, so this is as big as possible, and then you would, so sort of, if we make the analogy with our number system, you go 10, let's do it this way. When you're counting with our regular number system, you go 92, 93, 94, 95, 96, 97, 98, 99, and that's as big as you can get if you're only going to have 2 digits, and then it sort of spills over into the next digit. Well, after this, it spills over and would be 1 times 6 factorial, and that would get you 720. So it's nifty. All the numbers can uniquely be written, or all the positive, non-negative integers can be uniquely written this way, which is just, a nice little fun fact, and it's what makes it an actual number system. And there's some other exotic number systems, but I'm going to stop talking about them and continue doing the question. So B, write 6, 5, 3 in this form. Okay. So, 6, 5, 3. Well, now we're not going to exploit the fact that we know this can be done uniquely. I mean, we'll get this answer, and this will be the only answer, but what I'm going to do is I'm going to count the number of 5 factorials. So this is 600 plus 53. I don't need to explain where this 600 came from, because I will just turn it into 5 times 5 factorial plus 53. So now I need to write 53 using 1 factorial, 2 factorial, 3, and 4. So what I'm doing here is I'm just saying, well, how many 5 factorials can fit in here? And if you wanted to, you could actually write out this process. I'm not going to. How many 24s can fit in here? Well, 48 is less than 53, but 72 is not. So I can get 2 4 factorials. And what happened? We're left with 5 here. Now that's less than 3 factorial, which is 6. So we'll have 0, 3 factorials. We'll still be left with 5. And then we can get 2 factorials, which would account for 4, and then 1, which is just 1 factorial. So there we go. And there's not a whole lot to say about that if you wanted to describe the process. And once again, I'll just describe the process to you. I've got 653. I take my biggest factorial that I'm allowed to work with, in this case 5 factorial, and I ask how many 5 factorials are there. Okay, it's just like if I verbally said something like 7, how can I write 7 in binary? Well, I take the biggest power of 2 that's less than 7 and say how many 4s can I add up to and still, or can I have and still be less than 7? 1 4. Okay. Well, how many 5 factorials can I have and still be less than 653? 5 of them. So I get 5 times 5 factorial plus the remainder. And then I do the same thing to the remainder. How many 4 factorials are less than 53? Well, you can get 2 4 factorials, but the second you try 3 factorials, you're too far. So 53 is 2 4 factorials plus 5, and then we break it down and say, well, how many 3 factorials go into 5? And that's all it is. Okay? So, number systems. But that's B part. I don't really think you need to explain it a whole lot, but if you wanted to, add some sentences in, as I have just verbally done. Okay, so A is usually, quite an easy one. B can be a little harder. C, and if there's a D especially, will be more difficult. You'll actually have to understand the concept that they have presented up here, and you'll usually have to have a proof and some investigation on your own. C part, prove that all integers n, where n is between 0 and the number that we figured out in A part, which I'll just remind you was 719, can be written in this form. Okay, and while we're at it, let's also read D. Determine the sum of all integers n that can be written in this form with c equals 0. Okay, so the other numbers are allowed to vary, but c isn't. C has to be 0. Okay. What are we going to do? Prove that all the numbers can be written in this form. Okay. How would I go about doing that? Because I can't just sit down and test all 719 numbers. I don't have time for that. And even if I did, I wouldn't want to. It'd be boring, tedious, and I'd likely make a mistake. So, I think it might be a good idea to sort of... I feel like there's probably going to be a proof by induction or something on this. And I also think we could probably do a very general one. If you'll indulge me, I think I'm going to be kind of a bit more general. So what I'm going to do is a grander proof. You don't have to do this. You can just do what I'm about to do, but only have A, B, C, D, and E. And just for people who want to do things like this, you don't lose marks for being more general, being more mathematical, being more abstract, as long as you are correct, and at the end you say, oh, and the special case that you asked before, C follows by taking this number is this number is this, and things like that, which I will do at the end here. But I think I can go for the much grander question, which is, we will show all numbers from from n between 0 and, let's say, k factorial minus 1. Can be written as n equals a1 times 1 factorial plus a2 times 2 factorial plus a3 times 3 factorial, all the way up to, oh, I'm going to change this to k plus 1. So that way I can say ak and k factorial. Okay. First of all, I'll just make the note. If k equals 5, this proves C. Okay. And you might say, well, how would you know to do this? How would you know to set it up like this? Okay. One, it's a bit of experience. Two, we can use a little bit of stopping and investigating and show this actually does work. So what I'm going to start off by doing is just explaining, why do I want to do this? And I'm explaining this to you. I'm not explaining this on the contest. But take a look at the what numbers can be written without the 2 factorials, 3 factorials, and so on. 0 is 0 times 1 factorial. 1 is 1 times 1 factorial. Okay? But the second I want to go to 2, I've got to go to 0, 1 factorials, and 1, 2 factorial. And then we go to 3, that would be 1, 1 factorial, and 1, 2 factorial. And then we go to 4, 5, and you can notice a pattern, the 1s are alternating. But the second I want to go to 6, well, I can't do 3, 2 factorial, that's too big. Oh, I also need to have up here, and each AI has to be between 0 and I. There we go. We get 0, 1 factorials, 0, 2 factorials, and 1, 3 factorial. And so this down here is a very natural way to sort of investigate what's actually going on with these n's. How can I actually write all these n's out? So we start making a list and we start noticing patterns. And one of the patterns we might notice is, okay, when do I need a new factorial? Well, we go from 1 to 2. 1 is 1 less than 2 factorial. We go from 5 to 6. 5 is 1 less than 3 factorial, which is 6. And you can start to realize that. Other patterns that we can realize, well, 2 is just 0 plus 2 factorial. 3 is 1 plus 2 factorial. 4 is 0 plus 2 factorials. And 5 is 1 plus 2 factorials. So, in a sense, we're sort of repeating this block over and over and over. And so, that's why I think we can prove this by induction. Okay. So, I'm gonna... So this is my general statement. I'll get rid of this star here, actually. So every n can be written this way with these a1s, a2s, and they're in this particular range. We can go up to ak, k factorial. So, how do we do a proof by induction? Well, we first do a base case. And I'll say this is when k is 1. Okay? Can we actually write every number between 0 and... Actually, do I want k is 1? Yeah. 0 and 1 plus 1, which is 2 factorial minus 1. So every number between 0 and 1, can this actually be written in this form? Absolutely. 0 is 0 times 1 factorial, 1 is 1 times 1 factorial. Okay, base case is proven. It works. Okay, now assume this holds for any k value. So what are we assuming? We're assuming that n in this particular range is can be written as a1 times 1 factorial plus a2 times 2 factorial plus ak times k factorial. With each ai between 0 and I. Now, from this assumption that k works, we'll prove the k plus 1 case, or the k plus 1 statement. Okay. So let m be between 0 and k plus 1 factorial minus 1. Okay. Let's say this. Okay. Then m is strictly less than k plus 1 factorial, which is k plus 2 factorial, which is k plus 2 times k plus 1 times all the way down to 2 times 1. But notice this part here is just k plus 1 factorial. That's the definition of it. So it's k plus 2 times k plus 1 factorial. Okay. So m is less than this value. So we can find a value, let's call it a k plus 1, which is less than k plus 2. So that m is between ak plus 1 times k plus 1 factorial and then ak plus 1 times k plus 1 factorial. Okay. So that's good. And let's just use a little bit of color because I've been doing a lot of writing. Let's just explain that, therefore, this ak plus 1, if it's going to be less than k plus 1, then it's got to be less than or equal to k plus 1. Ooh, that's that condition that 0 has to be less than or equal to I, or ai has to be less than or equal to I. Notice that if I define n to be m minus ak plus 1 times k plus 1 factorial, then, well, what happens when I subtract ak plus 1 times k plus 1 factorial from this side? I get 0, less than or equal to m subtract this amount by definition is n, less than, and we'll get 1 times k plus 1 factorial. So 0 less than or equal to n less than or equal to k plus 1 factorial minus 1. Oh, but this right here is the base, or the assumption that we made that this works for k. So by assumption, on k, we can find a1, a2, all the way up to ak, so that each of these ai's is less than or equal to I, and n is a1, 1 factorial plus a2, 2 factorial, yada, 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 up to ak, k factorial. Okay, and then that tells me that m is a1 times 1 factorial plus a2 times 2 factorial, all the way up to ak times k factorial. So this is the n part of it. And then how did we get n from m? We subtracted off this a k plus 1 times k plus 1 factorial. And we know that for each of these, for these ones up here, ai is less than or equal to I, but we also observed on the last page that ak plus 1 has to be less than or equal to k plus 1. So now that we've proved a base case, and by assuming that the k situation is true, we can prove the k plus 1 situation is true, which we just did. We get to conclude by the principle of mathematical induction, which if you're not familiar with it, I would suggest you look it up online. You can get a lot of practice out there. I might even start to make some videos about how to do proofs with mathematical induction. But, it doesn't come up a whole lot on contests, every once in a while. So by mathematical induction, we have shown that our statement holds for all k. Okay? And what statement was that? We had it a couple pages ago. There's our base case. So what statement is that? That's this statement up here, which we'll highlight in green. I shouldn't have highlighted that in green. I just ran through the whole thing, but there we go. So for all numbers n between k plus 1 factorial minus 1, it can be written as a1 times 1 factorial, a2 times 2 factorial, a3 times 3 factorial, all the way up to ak times k factorial, with each of these ai's being between 0 and I. Okay, so we have now proven that's true no matter what k. And it just so happens that, and we already remarked this, and if you didn't, you should remark it at the end, or even just remind them at the end. Specifically with k equals 5, this statement works, because you get a times 1 factorial plus b times 2 factorial, just slightly different names for our coefficients. Okay? But that's all it is. And that proves c. You don't have to do this general form, but it's just going to be sort of a bunch of proofs by induction if you want to get up to 5 specifically. Okay. And I like being general whenever possible. It shows that there's more going on with these questions than specifically the numbers that they have chosen. Okay, now D part. Determine the sum of all integers n that can be written in the form with c equals 0. Okay. So really, what we're asking for is... So I think... So we don't want to just say, well, what numbers have 0 for our 3 factorial. I think it's more important to say, okay, 0 is 3 factorial. So sometimes A will be 0 and 1, sometimes B will be 0, 1, or 2, and so on. And add them up with how many 1 factorials do you have? How many 2 factorials do you have? I think that's going to be the right approach. So what do we want to say? How many... So we'll start D here. How many n have c equals 0? By the way, I didn't have to prove uniqueness, right? No, in C, just written in this form, not uniqueness. How many n have c equals 0? Okay, well, if n is a times 1 factorial plus b times 2 factorial plus c times 3 factorial plus d times 4 factorial plus e times 5 factorial. And we'll change the c to a 0. We have two choices for A, 0 or 1. 3 choices for B. We would have 4 choices for C, but we don't. C is fixed. We have 5 choices for D and 6 choices for E, 0 all the way through 5. So that tells me we have 2 times 3 times 5 times 6. 30 times 3 is 90 times 2 is 180. Such n. Now, we didn't actually show that this form is unique, and maybe that might be worth a mark. I think that's asking a little much from a grade 10 contest, but I think we could say something like so I'm gonna move this over here. Okay, so here's our D part, but I'm going to, in between C and D, I'm just going to remark that for n in this particular range, the range we just proved, we just used in the last question, we know that we can write it as this form. But here we have k plus 1 factorial such values of n. 0 through 3 is 4 numbers, because 3 is 4 minus 1. So we know we can write this out, but there are I plus 1 choices for each AI. Remember that each AI has to be between 0 and I inclusive, and so we just add 1 for the 0 that's being counted. So there are 1 plus 1 times 2 plus 1. So these are the choices for A2, these are the choices for A1, all the way times k plus 1 choices for AK, which is actually just 2 times 3 times 4 times k plus 1. But any number is the same if you multiply it by 1. So there are k plus 1 factorial possible expressions. Each number can be written in this way, so since number of n happens to equal number of possible expressions, and we know each n has such an expression, we can conclude that for any expression that determines an n, and for any n that determines a unique expression. So I'm just going to write that the expressions are unique. And you might say, why are you bothering with this? I don't think you really needed to do this for a mark, but when I say down here that there are 180 such n, how do I know? How do I know that 167 can't be written one way, but also another way? What I'm counting here when I say A has 2 choices, B has 3 choices, D has 5 choices, E has 6 choices, I'm counting the different expressions. No one came along and said, by the way, each expression gives you a different number. The question never told us that. Never at all. So, if we're going to use that fact, if we're going to say there's 180 numbers that I'm actually counting, and I want to count each of these numbers, I want to add them all up, I do need to point out probably that each expression gives me a different n. So there really are 180 numbers that have C as 0. Okay? You don't want there to be any overlap, and it turns out there's only 90 that have C as 0, because there's some sort of weird double counting going on, and you're actually going to add up each number twice when you don't need to. So you got to be careful with that. As I say, I don't really think this was probably worth a mark, but I mean, it is 4 on the contest, so it is the hardest question. But then again, it's the grade 10 contest. From experience, they don't ask the grade 10 and grade 9 students to be that rigorous. But better safe than sorry, and we've remarked that. So there are 180 such, let's actually say, expressions, each giving a different n. Okay, and how do I know they each give a different n? That's what this page was proving. Okay, and if you're interested in that, by all means read it. I mean, you probably watched it. But there we go. So we have 180 of these numbers. So, of these 180, 90 have A as 0, and 90 have A as 1. Of these 180, 60 have B as 0. 60 have B as 1, and 60 have B as 2. And you're saying, how do you know this? Well, consider so how did we count it when C was fixed? Well, we just counted up the number of possibilities for things that we weren't pinning down. So if I want the number of possible things that have D as 2, for example, well, we let everything else vary. So how many choices for A are there? 2. How many choices for B? 3. How many choices for E? 6. 2 times 3 times 6 is 36. Okay, that's the number of possible. That's the number of n that have C as 0 and D as 2. But how am I doing these in my head so quickly? There's nothing that says A would prefer to be 0 or more of the A's have 0. Half of them should have 0, half of them should have 1. A third of the 180 should have B as 0, a third should have B as 1, a third should have B as 2. So that's another way to say it. And you do it either way, do it expression-wise and say, well, how many have D as 2, but you don't want to write all that out. So you might just say a third of them have B as 0, a third have B as 1, a third have B as 2. So D had 5 choices, a fifth. And a fifth of 180 is 36. So 36 have D as 0, 36 have D as 1, D as 2, D as 3, and D is 4. Of the 180, so now I divide by 6. 6 different choices for E. 30 have E as 0. 30 have E as 1. 30 have E as 2. 30 have E as 3. 30 have E as 4. And 30 have E as 5. One sentence explaining one of the cases, like the A equals 0, A equals 1 case, and then just clearly writing them all down is enough. You don't have to justify each one of these, as long as your numbers are correct. Okay, so we have, the sum of the n's with C is 0, we're never going to add up any of the 3 factorials, but we'll get 90 0 times 1 factorials and 1 times 1 factorials. Okay, 90 for each possibility. We'll get 60 0 times 2 factorials. And yeah, I know you could drop the 0 factorials, but I'm just trying to make it connect to what I had just written down for them. And we've got one more to go. 30 and then we'll just simplify this. Okay, So this is 90, 0, and then 1. So this is 90 times 1. 60, 2 and 3, sorry, 2 and 4 is 6. 36 times 24, 48, 72, and what am I thinking here? It's a 96. I suppose I could just say 10 times 24, because 1 plus 2 plus 3 plus 4 is 10. So 240. I guess would be the fastest way. 31 plus 2 plus 3 plus 4 plus 5 is 15. 15 times 120. That should be 1... well, we'll do it slowly. So that'll be 600 for 5 times 120, and then... Okay, yeah, so it was 1,800. All right, now we just simplify this. So 90, 360, 36 times 240. Now we'll just do it slow again. Really trying to avoid busting out a calculator. 4, 2, 144, 72, so 4, 6, 8, 864, is that right? I guess it is. 8640, and then 3 times 18 is going to be 54000. Right? Yes, okay. And... yeah, so that's all we need there. And then we just add them up. It's going to end in a 0. 4 and 6 is 10, 9, so we'll carry a 1. 1 and 3 is 4, plus 6 is 10, plus 4 is 14. Carry a 1. 1 and 8 is 9. Oops, got my digits wrong. So 4 and 6 is 10. There is no hundreds digit here. So it's 0, carry the 1. 1 and 8 is 9, plus 4 is 13. 3, carry the 1, 6. There we go. 63,090 is going to be my final answer. Okay. So, that's it for D part. I'm just going to get out my calculator really quickly and double check these numbers before I end the video. 15 times 120. Yep, got that right. 36 times 24, got that right. And then 90 plus 360 plus 8640 plus 54,000. Yeah, everything looks good. Just double checked it with a calculator. I do try and avoid calculators when I can, just in case you guys forget your calculators. This is all still doable without calculator. Assuming, so the calculations were correct. This is assuming, of course, my reasoning is correct, but I think my reasoning is fine. We figured out how many numbers have c equals 0, and then we broke it down. We didn't try and add them all up. We didn't try to write them all out, but we broke them down into, well, some of them have 0, 1 factorials, some of them have 1, 1 factorials. We just want to add up the 1 factorials, add up the 2 factorials, and so on like that. Okay. So, that's really it, I guess. That's question number 4. So we're done the 2009 Galois paper. Yay! And up next will be the 2010 Galois paper, or the 2009 Hypatia, if you're interested in a bit more of a challenge. If you're looking for a multiple choice contest, of course, the Kaylee is aimed at grade 10. There's lots of sort of things. Feel free to explore around my channel. But whatever you decide to pick, I will see you in the next video. Till then, take care.